Okay, in this demo, I will analyze data for the North and South malls data set that is in this data set. And so I'll try to answer a couple of questions based on a scenario. So the scenario is the following. A new vegan hot dog producer wants to establish a kiosk in one of two malls, in the north and in the south part of a city. To test the market, the producer provides free samples in both malls and asks customers how much they would be willing to pay for the hot dog. Questions. In which mall, north or south, should the kiosk be established? And at what price should the hot dog be sold? The variables that I have, so what I'm going to be doing here is a comparison of means or a type of analysis. This is similar to a t-test or an ANOVA analysis. And what I will want to do is to find out if the difference in means between the North and the South Mall in terms of willingness to pay for the hot dog is significantly different. This can be done by having two variables. One variable uh, stores the location of the data collection. And this variable is dichotomous. It has two values, one for the north mall and zero for the south mall. And the other variable stores the payment, amount willing to pay for vegan hot dog. And this data has been obtained by individuals that just went to these malls and they asked a number of people to answer how much they would be willing to pay uh, for a hot dog that was given to them for free as a sample, as a free sample. And here's the data. So you have North Mall, that's all ones. And as you go down, you get South Mall, it's zeros. And there is 1 0 for amount to pay, which means that the person ate the free sample and said, I would not pay anything for this. I would have it for free, but I would not pay anything. There is no negative value here, but if there was a negative value, that would mean that the person who received the free sample said something to the effect that you would have to pay me to eat this hot dog. I would not pay anything. I would have to be paid to consume the hot dog. So, um, and I have some labels here that I'm going to include just to demonstrate how labels can be used in an analysis. So I already read my data into WarpPLS. So the data is here. So I already read that data from the spreadsheet. So I executed steps one, two, three. I read the data into a project file that has the same name as the data file. Now I will create my model and I'll create two variables. One is that variable, mall, north 1, south 0, and the other is amount that the individuals who received the sample dataset were willing to pay. And I'll create a direct link among these two variables. And I'll save my model. The software always asks me if I should check if I want to change the inner model analysis algorithm, and I do want to change, I would change it to linear. In outer model analysis algorithm, since I have only one indicator per latent variable, then I would just use the simplest algorithm, which is robust path analysis. I'll save my settings and I'll run my analysis. So we have a positive and statistically significant coefficient. So there is a difference between the means um, for payments in the North Mall and the South Mall. And since North is assigned the number one and South zero, this is how you create a dichotomous variable. That means that if it is in the North Mall, payment is willing to the payment that's willing uh, the amount that is the receivers of the free samples are willing to pay for the hot dog is goes up, is higher. So this means that in the North Mall, the average amount they are willing to pay is higher. So this is how you can do the equivalent to a t-test or an ANOVA analysis with structural equation modeling with WarpPLS. The advantage of this approach is that I can add more variables. I can add control variables here. If, say, I want to control for the gender or age, the biological sex or age of the respondents, I could have these variables here pointing at payment, and that would turn this analysis into more like an ANCOVA type of analysis. And these variables could aggregate other variables so they could be latent variables. So in other words, with structural equation modeling, I can do any of the most widely used tests in statistics because structural equation modeling is a general case of all of them. So there are special cases of structural equation modeling. And this applies to path analysis, multiple regression, MANOVA, ANOVA, ANCOVA, MANCOVA, t-tests. In all of these analysis, if I employ WarpPLS, I do them in a robust way, meaning that not all the variables have to be normally distributed for me to be able to trust my results. So here's this positive and strong and statistically significant coefficient and strong coefficient tells me that there is a difference in the amount willing to be paid, that people are willing to pay for the hot dog in the north and south malls. Now, the question here, the questions are: in which mall, north or south, should a kiosk be established? The answer is the North Mall because you will get a higher pay for your hot dog and you have a higher profit, assuming that the cost of establishing the kiosk is not so much higher in the North Mall, which may be the case. But since this is not part of the scenario, I'm assuming that the cost of the kiosk establishment is not much different for the two malls, but clearly the willingness to pay is much higher for the North Mall, which could be the reason for this is possibly that the North Mall is a fancier mall with that attracts more bigger spenders. Now the second question is: at what price should the hot dog be sold? And to answer this question, I'm going to go to data and correlations in descriptive statistics. And here I have a number of values. I have for payments, which is the most relevant here. So I have average payment, I have standard deviation in payments, minimum, which is zero, and maximum is 13. That's a maximum value that people would be willing to pay for the hot dog. Median, which is if I split the sample into two parts, right in the middle, that's the median. So it's a bit different from from the mean, which is the average. Uh, Mode is the most common value. Skewness, excess kurtosis, and I have here the histogram. So this variable here passes two tests of normality, so it's normal, but this variable here is clearly not normal, and yet that does not influence my results because we use a uh, robust algorithm to calculate standard errors and p-values, so I can trust my results. But to answer the question, I would argue that the best answer is the mean in the overall sample. I could easily calculate the mean for the North Mall, but it's likely that it's going to be a little bit higher than the mean for the entire sample. If I use the mean for the entire sample or the median, I would say the mean, the average for the entire sample, what I will end up doing is underpricing a little bit, which could potentially increase my sales in the North Mall because people are willing to pay more in the North Mall. So I would argue that this is a good answer to the second question. So at what price should the hot dog be sold? The answer would be $6.5. $6.50. If you were to adopt the median, that would be $6. Now, let me show how labels can be used. So I would just uh, store this into the clipboard, the entire data set. So the labels are text columns. And in WarpPLS, I can read them, but only one column at a time. And I read them into WarpPLS by going to the option Modify, and then I can add labels from file or from the clipboard. I can do it. I will do it from the clipboard, but only one column at a time. So I will go, and the software even says can be read, but only one column of labels can be read at a time. So you can add multiple of those columns, and they are text, essentially text identifiers. And so you can add multiple of those, but one at a time. So I'll click on OK, and the software will just give me a wizard, and I will just click Next and Enter, and here it is. So it's essentially text telling the software whether it's the North Mall or South Mall that we're referring to. So I read, and then I can show those labels in graphs. So if I go to this one, view plot, linear and nonlinear relationships, and if I go to uh, relationship graphs with data points and legends, I can then show those legends by changing the display options and then using the option data labels and then mall and then save settings, and this is the legend here is this is data for the North Mall and this is data for the South Mall. Now if I were showing relationship graphs with data points and labels, not legends, uh, this would be more or less how it would be viewed. So here's not, I guess, not so useful um, because the data is really split into two groups, and this is pretty obvious. But there are other situations in which having data labels can be quite useful. In fact, let me see if I can find one of those here on the web that I published in the past. So this is an example of a graph that is from a blog that I write, Health Correlator, and so this in this particular analysis, which was done with WarpPLS, I actually use data labels to identify each data point uh, uh, as associated with its US state. So this is a plot of latitude and cancer diagnosis per 1,000 people. And then I have data from all states in the United States. And the point here of this graph is to show that as latitude goes up, cancer diagnoses tend to go up, which it's could be interpreted as meaning that in sunnier states with lower latitude, you have higher levels of vitamin D because of more exposure to the sun, and then lower cancer diagnosis per 1,000 people. So this is an example of the use of data labels that is more the use of data labels is more instructive, is better. Now going back to our analysis for the mall data, it's always a good idea. It's always important actually to go to latent variable coefficients and look at the focal linearity variance inflation factors, which are they are the same here because I have only two variables in the model. But I don't want these numbers to be greater than 10, which would distort my results and make them less reliable or less credible. So uh, since these numbers are quite low, lower than 3.3, which is the lower bound of collinearity, below which it's guaranteed that there is no collinearity. Um, so this tells me that these data, these two variables measure different things. If they were collinear, meaning that the FCVIFs for one or both were greater than 10, that would mean that they are measuring the same thing. So a very strong association would be expected because they are collinear. They're measuring the same thing, but that's not the case. So they measure different things. So the strong associations is telling us that there is indeed an effect, and that is related to the location of the mall, the location of the kiosk, and the sampling of responses. So this concludes this demo on the mall kiosks data set.